The cases scenario stated that energy is obtained from the sun at the solar power facility at the desert. The Abercamp ESS will be then connected to the Lepster solar power plant. The power plant's energy will be then turned into chemical energy, which would be then stored as a chemical compound, so that it can regenerate electricity back for household and commercial use and be brought into the city. The engineer recommended using an octane to store energy as a result. However, a different company has patented the method of producing octane from carbon dioxide. Thus, we have come up with a suitable compound that is able to store and transfer energy to household but can still maintain its carbon neutrality. This project is closely related to the first law of thermodynamics that states energy can neither be created nor destroyed, but it can only be altered in form. It can be transferred from one location to another and converted to other forms of energy. In this case, electrical energy will be converted into chemical energy. Energy stored in the form of chemical compound can be readily converted into electrical energy for industrial and grid applications. Energy is released in the form of heat during combustion reaction of fuel and oxygen. In addition, the reaction will also produce carbon dioxide, which will contribute to global warming. Therefore, reversing the process will maintain the carbon neutrality. However, the reverse process of the reaction will be difficult and include the second law of thermodynamics that states total energy of a system and its surrounding always increases for a spontaneous process.
My name is Hayden. So now that you have learned the background of this project, however, what is the suitable chemical compound to replace the octane by maintaining the carbon neutrality, as octane already being used by the other company to avoid plagiarism? Secondly, how can we transfer the chemical compound from the desert power plant to the electrical power station to be transferred back into electrical energy? So now we are here with 5 objectives that we are going to achieve, which are: firstly, to produce a suitable hydro compound to substitute octane from carbon dioxide gas. Secondly, to determine the effect rate of the reaction. Thirdly, to determine the delta H, delta S for carbon dioxide hydrogenation. Fourthly, to determine the Gibbs free energy equation. And lastly, identify the kinetic and thermodynamic limitation. So,
that is able to substitute octane for energy storage is methane. Methane is a colorless, odorless, and also highly flammable gas. It is composed of 1 carbon and 4 hydrogen. The quantity of heat emitted during burning or combustion, as you may say, determines a fuel's heat value. Heat value, also known as energy or calorific value, which measures the energy density of a fuel and is represented in joule per kilogram. According to World Nuclear Association, energy content of methane is of range in 50 to 55 megajoule per kilogram. However, this is higher than energy content value of octane, which is 44 to 46 megajoule per kilogram. The gas concept involves chemically storing electricity from renewable sources as an energizing gas. Through this initiative, reaction between carbon dioxide and hydrogen, which is also known as hydrogenation of carbon dioxide, produces methane gas. Methane gas is easily stored and transferred in the natural gas network. It is being stored under high pressure at the refinery plant in the desert. It is then being transferred to the residential area through underground pipelines. Let's look at how methane is produced from carbon dioxide to maintain its carbon neutrality.
I will proceed with the unit process. In this project, we utilize electrical energy harvested from the solar panels, and then the electrical energy is fed into the electrolyzer, in which water molecules is divided into oxygen gas and hydrogen gas. In this part, oxygen gas and hydrogen gas in traces amount along with water vapor are present. So, to purify this gas, the first step is water vapor is condensed into liquid, and then the remaining water vapor is passed through the zeolite absorber, which is a dehydrator. Lastly, the pure oxygen gas is compressed and later stored. In this part here, also same with the oxygen gas, this part contain hydrogen gas and oxygen gas in traces amount along with water vapor. So for the first step, water vapor is condensed into liquid and then it is removed. Next, the reaction here is to remove oxygen gas, which is the oxygenation reaction. Oxygen gas is fed with hydrogen gas to produce water, in which the water vapor is later removed by passing through the gas to the zeolite absorber, which is also the dehydrator. Then the pure hydrogen gas is fed with CO2 gas, as we can see in the Sabatier reaction, to produce CH4 and water. Lastly, the water is removed from the product by passing through the gas to the zeolite absorber again. And then, as you can see here, all the water remaining are recycled, and this is the water supply towards the electrolyzer to produce more oxygen gas and hydrogen gas. As for the Sabatier reaction, this is the reaction happen to produce the methane gas. We have CO2 gas and hydrogen gas to produce methane gas and water. The pressure is 3 megapascal, and the presence of catalyst is nickel with the optimum temperature of 300 degrees Celsius to 350 degrees Celsius.
Hello, I am Naufal, and now we will move on to our project data analysis. For the first part, I will discuss about the factors that affect rate of reaction. The first factor is the concentration of reactant. In this case, carbon dioxide and hydrogen gas. If the concentration is high, the rate of reaction will be high because the number of particles per volume is high. Next is the temperature of the reaction. When the temperature is high, the rate of reaction increases because the kinetic energy of particles increase. Then, presence of catalyst increase the rate of reaction because it provides an alternative way to the activation energy, hence it lowers the activation energy. Lastly, high pressure can increase the reaction of the particles, as particles are closer together under high pressure. All these factors increase the effective coalition.
Next, I will explain about delta H0, delta S0, and analysis on Gibbs-free energy. The stoichiometry equation is CO2 plus 4H2 produce CH4 plus 2H2O. Then, this table shows delta H0 of formation and S0 for each compound in the equation. The delta S0 of formation is used in the formula to find delta H0, which we get negative 252.7 kJ. And then the S0 of each compound is used in the formula to find delta S0, which equal to 172.562 joule per Kelvin. And then we proceed to analysis on Gibbs-free energy, which is delta G0 equal to delta H0 minus T delta S0. From the calculation we did just now, the delta H0 and delta S0 have negative sign. By predicting using the sign, delta G0 can be either positive or negative, depends on the temperature. In high temperature, the delta G0 become positive and shows non-spontaneous reaction. In low temperature, the delta G0 become negative and shows the reaction is spontaneous.
Hello, my name is Jazzy. So now we move on to our next section of data analysis, which is to identify the kinetic and thermodynamic limitation of the reaction. So first of all, in terms of kinetic, temperature must be high, so the rate of reaction will also be high. Wherever for thermodynamics, the temperature must be low to make the reaction spontaneous. But the thing is, how do we know whether the temperature is the right value? So basically, we need to use the formula, which is the Gibbs free energy. So by using the formula, we plug in all the information that we have gained to find the ideal temperature. So as shown in the calculation, the border temperature between high and low temperature of the reaction in terms of thermodynamic is 343 degrees Celsius. So if the temperature is higher than the temperature calculated, it will lead to non-spontaneous reaction. So from the calculation also, the max temperature for the reaction to stay spontaneous is in the range of optimal temperature of Sabatier reaction in terms of kinetic, which is between 300 and 400 degrees Celsius. So from the reaction, we can conclude that the temperature satisfies both thermodynamics and kinetic limitations.
So for the conclusion, all in all, the objective of this project have been achieved, which are producing a suitable energy-bearing compound from carbon dioxide to substitute octane. This is because by using Sabatier process, methane can be produced from reaction of carbon dioxide and hydrogen gas at optimum of 300 Celsius to 350 Celsius and 3 megapascal. Energy from solar plant is utilized to produce pure hydrogen from water, which then carbon dioxide is supplied to produce methane. Methane gas is transferred via underground pipeline system from power plant in the desert to power station near residential areas. However, some factors must be taken into consideration during the project as it might affect the rate of reaction. These factors are concentration of reactant, presence of catalyst, temperature and pressure of reaction. Delta H, delta S for carbon dioxide hydrogenation reaction was determined, as well as analyzing Gibbs free energy equation and identifying the kinetic and thermodynamic limitation. Based on the calculation, the delta H reaction and the delta S reaction are negative 252.7 kJ per mole and negative 410.392 joule per Kelvin respectively. Since both values are negative, the gate free energy of this reaction will be spontaneous at low temperature and non-spontaneous at high temperature, with high temperature border. Since both values are negative, the gate free energy of this reaction will be spontaneous at low temperature and non-spontaneous at high temperature, with temperature border of 343 Celsius. The reaction should be conducted at high temperature as possible, however it must not exceed the limit as the reaction will be non-spontaneous. It requires more energy from surroundings. That's all from us. Thank you and I hope you all enjoyed the presentation.